So this was all about set theory. Now we'll move on to relations. So the first point about relation is a relation R on a set X, which we can also write like that is R is X cross X. Okay. Now this is, we have three properties for relation. It may be reflexive, it may be transitive, it may be symmetric. Actually four properties, and it may be equivalence. There are four types of relations. First, reflexive, transitive, symmetric, and equivalence. Reflexive, the condition is if there is an element x, small x, Rx. X is related to another x, and for all small x belonging to x. Fine. Transitive, if, let's first draw symmetric, if x or y, x is related to y, and this implies that y is also related to x for all x and y belongs to x. Fine. Transitive, if x or y, comma y or x, that means comma y or z, and this implies x or y means x is related to y or z means y is related to z, and if these two implies x is related to z, this means the relation is transitive. R is transitive. Okay. For all x, y, z belongs to x, and it will be equivalence if it is reflexive, symmetric, and transitive. Fine. Let's see one example. Let's have a set X as 1, phi, 1, 1. Fine. Now, to see the reflexive condition, we will see X R X. That means if this is Rx, then do we have any X Rx or not? Okay. So 1 is related to 1 in here. That's why we have an X Rx condition. So this set X is, this relation R is reflexive. Okay. Reflexive. To see the symmetricity, we have XRY and YRX. Of course, we have XRY, that is 1 is related to 1. Okay. In this case, X and Y are equal. And we have YRX because 1 is also related to 1. So that's why this is symmetric also. What about transitive? 1 is related to 1, XRY, 1 is related to 1, YRZ, 1 is related to 1. So that means 1 is related to 1, and we have this as transitive also. Okay. So this means if this is all the three, then it will be equivalence relation. Okay. Let's see one other example to make it clear. Let's say X is 1, 2, 5, 1, 1, 2, 2, 1, 2. Okay. Let's say we have this set as X. Now XRX is, if this is X, XRX is present. If this is X, XRX is present. Fine. For phi, XRX is also phi. So for phi, XRX is present. And we have one other element. That doesn't matter. So it is reflexive because it satisfies every condition of reflexivity. Right. Now symmetricity, this is reflexive, right? Now for symmetricity, symmetric relation, if we have 1, 2, that means if we have X or Y, that implies Y or X should be present, but we don't have any 2, 1 element in here. That's why this is not symmetric. But if we add this element in this set, we have a symmetric relation. We will have a symmetric relation. Okay. Now for transitivity, if let's say transitivity, if we have X or Y and Y or Z, then we must have X or Z. Let's say if we have 1, 2 and if we have 2, 2, then we must have 1, 2. We have it. If we have 1, 1 and if we have 1, 2, then we must have 1, 2. Because X or Y and X is related to Z, so that's why 1 is related to 2. And we have 1, 2. So this is transitive. Fine. So, but it is not equivalent until we add this element in this set. Okay. So if we add this element in this set, then we will have, of course, then we will have an equivalence relation, because it will satisfy all the three properties: transitivity, symmetricity, and reflexivity. Okay. Now let's move on. This is the most important thing in relations. Except this, nothing is asked. So we'll move on to functions. Okay. For functions, let me draw first four relations. First is 1, 1 onto function. 1, 1 onto function is, let's say we have two sets A and B. A has 1, 2, 3, 4 element, and B have A, B, C, and D. Okay. If one is related to, let's say, A, 2 is related to B, 3 is related to C, and 4 is related to D, then it is a 1, 1, 1, 1. Why 1, 1? Because every element is related to another element, and one element is related to one element. Okay. Now here, second element is related to second element. Not the position doesn't matter, but it is related to only one element, not two elements. Okay. It is not like this. Okay. So this is 1, 1 onto. Why onto? Because nothing is left in this set, in set B, because we have R from A to B. Okay. Relation is from A to B. That's why this is 1, 1 onto function. One other name for this is bijective. Bijective. Why bijective? I'll tell you. Let's move on to the second one. Let's mark it first. Second one will be 1, 1 function, not onto function. Okay. So it's just 1, 1 function. Okay. Not onto. Just keep in mind. So 1, 1 will be 1, 2, let's say 3. You have A, B, C, and D again here. Now 1 is related to 1, 1 is related to 1, 3 is related to D, C, let's say. Now this is our set A and this is our set B. Now, as this element is left out in set B, so there are not all elements in B which are related to A. Okay. Or you can say there is not an element which is related to B. Okay. So that's why this is not onto. Okay, you have to just see the range, the codomain set. Okay, if anyone is left out here, then it will be not onto. That is called an into function. Okay. Now this is 1, 1 because all the elements are related, is connected to only one element in the other set. Third type will be many one onto function. Many one, as again the name suggests, many are related to one element, and onto, that means there is no element left in the B codomain set. Okay. So we have this 1, 2, 3, 4, A, B, C. Now let's say 1 is related to A, 2 is related to B, 3 is also related to B. Okay. And 4 is related to C. Now there are two elements which are related to 1. Let me use another pen. There are two elements, 2 and 3, which are related to only one element, which is B. So this is many because there are more than one which are related to 1. Many to 1, and why onto? Because there is no element left in the B set. Okay, B set. There is no element. All the elements are connected to one of the element of set A. So this is many one onto function. Okay. Oh, one thing I forgot. 1, 1 function is also called injective. Okay. Fourth type of function is many one into function. Okay. Many one into function. What this says is, let's say we have two sets A and B. We have, let me just slice it up. Okay, we have elements as 1, 2, 3, 1, 2, 3, and here we have A, B. If it is into, then C and D. Okay. Now, let's say 1 is related to A and 2 is related to B, let's say, and 3 is related to B, C and D, or you can say 3 is related to A and D. A and D. Now this is into because C is left out here in the set in the codomain range, and 3 is related to 2 of the elements in the set B. That's why it is many one and into function, not onto. Not onto means into. I explained it earlier, and that's why this element is left out. That's why this into function, okay, and many one. And of course, this one here is 1 into function, okay, because it's not onto. So let's move on to the next page. We have another property which is very important with respect to ITJE, okay, that is root of x square is mod x. Never write x as the root of x square. That's not true, okay. Root of x square is not x. Wherever you find this type of things, most probably in complex number, but I am telling it here. So you will just do mod x, okay, and you will then add mod. You will then open mod, okay. So now next point is about periodic function. Periodic functions means what? It has a period. After each period, after every period, it will repeat itself. So we can say f of x plus t, if you add a period to x, then it will be same after that x, after that t. Okay. So in here, t is the fundamental period of which function? Fx, because we are talking about fx here. So let's see one example. Let's say we have sin x. Now everybody know the graph of sin x. Okay. It will start from here and then it will repeat. Again it will go back there. So after every this interval, let me draw it with another pen. This thing is again repeated here. Okay. This thing is always repeated. So this will be the time period of sin x, and which is 2 pi. Okay. So after every 2 pi, sin t is equals to 2 pi, sin of x, f of x is sin of x, so sin of x will be equals to sin of x plus 2 pi. Okay. Here t is the period. 2 pi can be related to this t. X plus t is equals to sin x, f of x. Okay. Now, there are two main points about this. Let me explain to you. First point is, if fundamental period, which we saw last time, that was t, if the fundamental period of fx is t, then the fundamental period of, these are two variations I am going to tell you about, the fundamental period of f of, let's say, ax plus b, that will be t upon mod a. Remember this mod a, because many times it is asked minus 2x, f of minus 2x, what will be the fundamental period, and people write 2 pi by minus 2, and that's why minus pi, but this is not true. Okay. So example, again you can take sin pi. Second point is, let t1 and t2, let's say we have two time periods t1 and t2, and these are fundamental periods of fx and gx. Two functions we have, fx and gx, and these are fundamental periods respectively, t1 for fx and t2 for gx. Then LCM, that is least common multiple, of t1 and t2 is the fundamental period for which function? C1, let's say any constant C1, f of x plus C2, another constant, g of x. Like you have, if f of x is sin x, okay, and g of x is cos x, so C1 sin x plus C2, let's say C2 is 1. So a period of this function will be LCM of T1 and T2. T1 is what? 2 pi. We just saw that. Cos pi, again 2 pi will be the time period. So the least common multiple of 2 pi and 2 pi, that will be the LCM of, that will be the fundamental period of C1 sin x plus cos x, or C2 cos x, anything. Okay. So this is the main thing. And C1 and C2 are arbitrary constant. C2 and C1, C2 and C1 are arbitrary constants. Fine. Now I'll move on to another point, which is about composite functions. Composite functions. Composite functions are the functions of functions. Okay. So let's say we have fx as f of g of x. Fine. It's also written as fog x for all x belong to domain of which function? F of x, capital Fx, not small fx. Okay. And another point about this is fog x is not equals to gof of x, except some cases which I'm not going to discuss, but keep in mind that this is not equal to g of x. Let's see an example. Let's say we have f of x is sin x and g of x is let's say x square. Okay. Now f of g of x will be what? F of g of x is what? X square. So f of x square. F of x is sin x. So f of x square will be sin of x square. So this is our fog x. Right? Now, what will be our g of x? G of f of x. That will be g of f of x is what? Sin x. Right? F of x is sin x. This f of x is sin x. G of sin x. G of x is x. G of x is x square. Okay. So g of x is x square. So g of sin x will be sin x whole square. Fine. G of x is x square. So g of sin x will be sin x whole square. That is also can be written as sin square x or gof of x. Now sin of x square is not equals to sin x whole square. Fine. And that's how we can prove that fog is not equal to gof. But you also need to know that f of g of x. How to find f of g of x? Okay, you might have something like f of g of f of x square, and you might have to solve this. So you have to just go in this direction, one step by one step. First of all, find f of x square, then g of that thing, then g of that thing, and then f of that thing, and you will finally get these type of functions. Okay, sin of x square or sin square x. This is the point about composite functions. Now we'll move on to graphs. So if you change the variable, what is the change in the graph of f of x? The change. Okay, so first one is if y is equals to fx and we change, we have to find the graph of y is equals to minus fx. Fine. So what it would be? It would be mirror image. This graph will be mirror image of graph 1. Okay, graph 1 is this along x-axis. Okay, you have to keep that in mind, that if you have y equals to f of x and if you have to draw y equals to minus f of x, then just draw mirror image of that y equals to fx along x-axis. Second point is, if you have y equals to fx, of course, as your primary functions, then the y equals to f of minus x will be mirror image of graph 1 along y-axis. Of course y-axis, because first one is x-axis, so there must be a y-axis if minus is shifted inwards. Okay, so keep in mind this is f of minus x and this is minus f of x. In this case you will change negative sign in x. In this case you will just put a negative sign outside fx. Now third case is graph of inverse function of y of x, that is, let's say y is equals to f inverse x, or we'll just put y equals to fx here, and let's say we have y equals to, we have to draw the graph of y equals to f inverse x. So this will be the mirror image of the graph along y equals to x line. Let me just draw it for you. It will be like, let's say you have some graph, this is our y equals to x line, you have some graph like this, so it will be the the y equals to f inverse x will be the, let's say this is y of f of x, y equals to f inverse x will be the mirror image along this line. Okay, what is the mirror image along this line? This. Okay, this will be the mirror image. So this is the function for, this is the graph for y equals to f inverse x. So you have to just keep in mind 3 points. That first, if you have y equals to fx, and if you have y equals to fx, and if you have to draw the graph of y equals to minus fx, just draw it along x-axis. You can take example like y equals to x. Okay, we'll just draw it, y equals to x. Now what will be y equals to minus x? This one. So you are taking mirror image along this axis, and this is x-axis. Okay, similarly for this f of minus x, in this case you can take sine of x. Okay, y equals to sine of x, sine of minus x will be minus sine x. Okay, and then you will see that this is mirror image along y-axis. Then we have third case as f inverse x. If you have the graph of y equals to fx and you have to find the graph of y equals to f inverse x, then we will just draw y equals to x line, and then you will just plot the mirror image of the function y equals to fx. Okay, and you will get the graph of y equals to f inverse x. Now next point is about number of functions. So number of one functions is equals to two cases, npm and 0. npm if m is less than equals to n, and where n of a is equals to m. Okay, let me just draw it once again. N of a is equals to m. Okay, such that these properties true, and 0 if m is greater than n. Okay, because if m is greater than n, npm cannot be calculated, and also n of b is n. Okay, we have two sets a and b, one functions, so there is one set a, there is one other set b, is related, they are related. Okay, now npm, number of one functions. How to calculate number of one functions? It will be npm, where n is the number of elements in b set, and m is the number of elements in set a. Okay, n of a, that is number of, there is cardinal number of set a. Okay, and this is the cardinal number of set b. Okay, now another point is number of onto functions. These questions are asked directly in the exam, that how many numbers of one function can you see in this function a or something like that. Number of onto functions will be 0, or you can say summation over r equals to 1 to m and minus 1 to the power n minus r, and if you have n minus r, then you must have ncr. Okay, you can remember it like that. If you have n minus r, then you have ncr and r to the power m. Okay, there are also two conditions. This will be if m is less than n. Okay, and of course this will be otherwise, that is if m is greater than or equals to n. Okay, so number of onto functions, you have to remember this formula, minus 1 to the power n minus r, ncr r to the power n m. Okay, where n and m are these two only, okay, which I specified earlier. Now next point for this is domain of function f is range. This is very important point considering IIT JEE, is range of f inverse. Okay, and domain of f inverse is equals to range of f. How can you remember this? Let's say we have two relations, two sets A and B. A is related to B by R and B is related to A by R inverse. Okay, of course R inverse. Then domain of f, or you can say as it is a function, we will have f and f inverse. Okay, so this is f related to f and this is related to f inverse. So domain of f, that is this, will be range of f inverse. Okay, because f inverse is from this to this, and range of f, that is this, will be domain for f inverse because f inverse is originating from it. So this will be the domain for f inverse, and which is range of f. Okay, so these are 2 points. You can remember it easily by just drawing the diagrams. And one more point we have, that is product of two even functions. Okay, I'm writing functions as this. Two even functions is even. Even function, you know, if f of x is equals to f of minus x, then this is an even function. If f of x is equals to minus f of x, that is if you change the variable x to minus x, and if you don't see any change, then it is an even function. If you see change just like this, that it changes to minus of f of x, then it is an odd function. Okay, so product of two even functions is even, and product of even and odd functions will be is odd. Okay, examples, even function f of x is f of minus x. You can always think of x square, or in trigonometric terms cos x. For f of x is minus fx, you can take x, and trigonometric terms sin x, tan x, everything, anything. Okay, so this is the thing. If product of even and odd, x and x square will be x cube, which is also odd. Any odd power of x is an odd function. Then cos x, product of two even functions, let's say x square and x square, so that will be x to the power 4, or cos x into x square, that will be x square cos x, that will give you even function. Okay, because when you will change x to minus x in x square, it will be again x square. Okay, next point, we'll move on to the next point, that is inverse of an equivalence relation. What is an equivalence relation? Let's just revise it. Equivalence relation is a relation which is reflexive, transitive, and symmetric at the same time. So inverse of an equivalence relation, it is also directly asked in the exams, is also an equivalence relation. Okay, now this will be just directly asked that if you have f as an or you can say r as an equivalence relation or x as an equivalence relation, what will be the x inverse? What relation would it be? Okay, they can just say you some examples that x is this 1, 2 and all of that, and they might ask you that this is given set B, which is x inverse. So will it be also an equivalence relation? Then you have to just think about this, that inverse of an equivalence relation is also an equivalence relation, and that's why this B will be also an equivalence relation. Next point, if cardinal number of set A is n, then number of relations from A to A, that is, let's say this is set A, this is also set A, number of relations from this set to this set. Okay, these are the relations R. So number of relations from A to A will be 2 to the power n to the power 2, that is 2 to the power n square. Okay, so if you have two elements in A, then 2 to the power 2 to the power 2, that is 2 to the power 4, that is 16. 16 relations will be there, 16 number of relations. If na is 2, then 2 to the power n square. Okay, next, number of functions from A to A. This is important. Number of functions from A to A, that will be n to the power n, that is in this case 2 to the power 2. Okay, if you have 3 elements, then 3 to the power 3. Okay, again functions, number of functions, remember this. Now again, number of 1 1 onto functions from A to A. This is important. Number of 1 1 and onto 1 1 and onto functions from A to A, that will be n factorial. You can see this is decreasing. First of all, in case of 2 it was 16, this was 4, and this will become 2. 2 factorial is 2. Okay, so you can see that if you change the condition, if you add the constraints like 1 1 onto, for relation it is function as a constant, and for function 1 1 onto condition is constant. So the factors goes on decreasing from 16 to 4 to 2. The number of relations functions they get decreased. Okay, so here is the whole theory for sets, relations, functions. We will continue with complex numbers. Thank you.